Space and time are not empty stages upon which the universe performs. They are the stage itself, an invisible framework that shapes every movement, every moment, and every structure in existence. Woven together into a single fabric, space-time forms the architecture of reality, stretching and bending in response to matter and energy. Every star, every planet, and even the flow of time within our own lives is guided by this hidden design. To understand the universe, we must look beyond what we see and explore the architecture that holds everything together, the silent structure upon which the cosmos is built. For nearly 300 years, we were content to live in Isaac Newton's universe. It was a world of absolute certainties, a world where space was an empty, unchanging box, and time was a steady, relentless clock ticking away at the same rate for everyone, everywhere. In this Newtonian world, gravity was a mysterious, invisible tug, a force that somehow reached across the cold, dead vacuum of space to pull on planets and stars. Newton himself admitted he didn't know how it worked, only that it did. He famously said he framed no hypotheses about the nature of this pull. To him, gravity was like an invisible rope connecting the Earth to the Sun, keeping us in orbit through a constant silent tension. It was effective, it was mathematically beautiful, and for centuries it was enough. But as the 20th century dawned, a young patent clerk in Switzerland began to feel that something was deeply wrong with this picture. Albert Einstein realized that Newton's gravity had a fatal flaw. It was instantaneous. According to Newton, if the Sun were to suddenly vanish, the Earth would feel the loss of its gravitational pull at that very same moment and fly off into the dark. But Einstein's own work on light had shown that nothing, not even information, can travel faster than the speed of light. If it takes 8 minutes for the Sun's light to reach us, how could we feel its gravity immediately? There had to be a delay, and if there was a delay, then gravity couldn't be a simple invisible rope. It had to be something else. It had to be a property of the environment itself. Einstein's journey to this realization began with what he called the happiest thought of his life. He imagined a man falling from the roof of a house. To the man falling, gravity would effectively disappear. If he dropped an orange, it would float beside him. He wouldn't feel his own weight. This led Einstein to a profound conclusion known as the equivalence principle. The effects of gravity are indistinguishable from the effects of acceleration. If you were in a windowless elevator in deep space, and the elevator began to accelerate upward, you would feel pressed to the floor. You would feel weight. Without a window, you wouldn't be able to tell if you were sitting on the surface of a planet or being pushed through the void by a rocket engine. This was the spark. Einstein realized that if acceleration and gravity were the same thing, then gravity wasn't a force pulling you down. Instead, the environment was pushing or warping around you. He began to envision space not as an empty void, but as a physical fabric, the space-time we introduced earlier. If this fabric were flexible, then matter and energy wouldn't just sit on it. They would change it. They would push down on it, stretching it and creating curves. This was the birth of an entirely new way of seeing reality. Gravity was no longer a ghost reaching through the dark. It was geometry. When you drop a ball, it doesn't fall because the Earth is pulling on it with a secret force. It falls because the Earth is so massive that it has warped the very space-time around it into a gentle slope. The ball is simply following the natural, curved path of the world it inhabits. It is rolling down the hill that the Earth's mass has carved into the fabric of the universe. Einstein's insight replaced the invisible tug with a tangible structural reality. He showed us that we don't live in a box, we live in a landscape. Every star, every galaxy, and even our own bodies are like weights placed on a vast cosmic trampoline. The deeper the weight, the steeper the curve. This transition from force to curvature was the most significant shift in our understanding of nature since the time of the Greeks. It meant that the universe wasn't a collection of objects acting on one another. It was a single unified structure where the container and the contained were inextricably linked. To understand gravity is to understand the shape of space-time. We are not being pulled by strings, we are being guided by the architecture of the cosmos. This realization didn't just explain why the planets stay in their orbits. It opened a door to a universe that was far more dynamic, more flexible, and more mysterious than anything Newton could have imagined. We are participants in a grand geometric dance, where every move we make is a response to the invisible curves that surround us. Gravity is not something the universe does, it is something the universe is. It is the visible manifestation of the geometry of existence. If we accept that gravity is the curvature of space-time, we must then ask, how exactly does this warping occur? To visualize this, we often turn to the analogy of a stretched rubber sheet, a cosmic trampoline. Imagine this sheet represents the 3 dimensions of space and the 1 dimension of time, all woven together. When the sheet is empty, it is perfectly flat. A small marble rolled across it will travel in a straight line at a constant speed. This is the empty universe of our intuition, where objects move undisturbed through a void. But the moment you place a heavy object, a bowling ball, onto that sheet, everything changes. The ball creates a deep depression. It stretches the fabric, pulling it downward and distorting the grid lines that were once straight. Now, if you try to roll that same small marble across the sheet, its path is no longer a straight line. As it nears the bowling ball, it begins to veer into the curve. If the marble has enough speed, it might swirl around the depression in a circular or elliptical path, just like a planet orbiting a star. This is the physical reality of the universe. The bowling ball is a star like our sun, and the marble is the Earth. The sun doesn't need to reach out and grab the Earth with an invisible hand. By its very existence, by its immense mass, the sun creates a permanent well in the fabric of space-time. The Earth, travelling through its neighbourhood of the solar system, simply encounters this well. It isn't being pulled toward the sun, it is trying to move in a straight line, but the straight path itself has been bent into a circle by the sun's presence. This warping is not limited to large objects like stars. Everything with mass and energy, from a mountain to a pebble, from a human being to a single atom, contributes to the warping of space-time. The more mass you pack into a region, the more severe the curve becomes. On Earth, we feel the curvature created by our planet as the sensation of weight. When you walk uphill, you are moving against the grain of the Earth's gravitational well. When you sit in a chair, you are being held in place not by a force, but by the fact that the Earth has tilted the floor of space-time beneath you. But space-time is not a 2-dimensional sheet. It is a 4-dimensional continuum. The warping happens in every direction simultaneously. Imagine a 3-dimensional block of transparent jelly. If you could place a heavy weight in the center of that jelly, the surrounding material wouldn't just dip. It would squeeze, stretch, and compress in a complex spherical pattern. This is what mass does to the universe. It creates a density of space and a dilation of time. This warping also affects light. Because light travels through space-time, it has no choice but to follow the curves that mass creates. If you shine a beam of light past a massive galaxy, the light will bend. It follows the dent in the fabric just like a physical object would. This phenomenon, which we call gravitational lensing, is one of the most direct proofs we have that space-time is a flexible physical structure. We can actually see the distorted images of distant galaxies because their light has been forced to navigate the hills and valleys of the cosmic landscape. The realization that mass warps reality changes our relationship with the world around us. We are not just standing on a rock. We are nestled in a curve. The atmosphere, the oceans, and the very ground beneath our feet are all held together by the shape of the space they inhabit. We live in a universe of textures. Some areas are flat and tranquil, while others are steep and violent. The architecture of space-time is a living, breathing thing, constantly shifting as matter moves through it, and we are forever caught in its embrace. In the Newtonian view, the motion of the planets was a battle of forces. The Sun pulled inward with gravity, while the planet's momentum tried to carry it away. The orbit was the result of these two opposing tugs, reaching a perfect balance. But in Einstein's curved universe, the motion of the heavens is much simpler and more elegant. There is no battle. There are no opposing forces. There is only the path of least resistance. Every object in the universe, from a speck of dust to a supercluster of galaxies, is trying to do the same thing: move in a straight line at a constant speed. This is the fundamental law of inertia. However, because space-time is curved by mass, a straight line is not what it appears to be. In the geometry of curved surfaces, the shortest, straightest path between 2 points is called a geodesic. Think of the Earth. If you want to fly from London to Los Angeles, the shortest path on a flat map looks like a curve. But on the curved surface of the globe, that path, a great circle, is the straightest possible line you can take. You aren't turning your plane. You are following the natural geometry of the sphere. Space-time works exactly the same way. When the Moon orbits the Earth, it isn't turning in space. It is traveling in what it perceives to be a perfectly straight line through four-dimensional space-time. It is the fabric it is traveling through that is curved. The Moon is simply following its geodesic. This concept removes the need for action at a distance. The Sun doesn't need to know where the Earth is to exert gravity on it. The Sun only needs to warp the space-time in its immediate vicinity. The Earth then responds to the local shape of the space it is currently in. Motion is not a response to a distant command. It is a response to the local environment. This is why gravity affects everything equally, regardless of what it's made of. A lead ball and a feather fall at the same rate in a vacuum because they are both following the same slope in space-time. The slope doesn't care about the mass of the object falling down it. This geometric guidance system explains the breathtaking clockwork of the solar system. The planets are not held in their tracks by invisible chains. They are surfers riding the waves of space-time. The intricate dance of binary stars, the slow rotation of galaxies, and the grand expansion of the universe itself are all governed by this principle. Objects move where the architecture of space-time tells them to move. It also explains why light is affected by gravity. If gravity were a force that only pulled on things with mass, light, which is massless, should be immune to it. But light is not immune. Because light must travel along the geodesics of space-time, it has no choice but to follow the curves. When we see light from a distant star, bending as it passes near the Sun, we are seeing the light following the straightest possible path through a warped environment. This view of motion as geometry brings a profound sense of unity to the cosmos. There is no distinction between the force of gravity and the motion of objects. They are two sides of the same coin. The universe is a vast interconnected network of paths, a map where the landmarks, the stars and planets, are also the creators of the roads. We are all travelers on these cosmic geodesics, following the natural contours of a reality that is far more structured and guided than we ever dared to imagine. To truly understand how we move through the universe, we must look closer at the concept of the geodesic. As we've seen, a geodesic is the straightest possible path through a curved space. But in the 4 dimensions of space-time, a geodesic is not just a path through space, it is a path through time as well. This is where the architecture of the universe becomes truly mind-bending. In our everyday life, we think of space and time as separate. If you want to meet a friend, you give them a location, space, and a time. But in the fabric of the universe, these are inseparable. When an object moves, it is moving through space-time. Therefore, a geodesic is a 4-dimensional track. It represents the history of an object, its world line. Imagine a satellite orbiting the Earth. In 3-dimensional space, it travels in a circle. But if you were to draw its path in 4 dimensions, with time as the vertical axis, the satellite's path would look like a long, stretching spiral or a helix. This helix is the satellite's geodesic. It is the straightest possible path it can take through the warped jelly of space-time surrounding our planet. One of the most startling features of geodesics is that they represent the path of maximum proper time. In the strange logic of relativity, an object following a geodesic, an object in free fall, is the one that experiences the most time passing between 2 events. If you were to drop 2 clocks from a high tower and one clock fell straight down, following its geodesic, while the other was pushed sideways by a rocket, the clock that fell naturally would record more time. Gravity and motion are not just about where you go. They're about how fast you age. Geodesics are the veins of the universe's structure. They tell us that there is a natural way to move. Anytime you feel a force, like the push of your car seat when you accelerate or the floor beneath your feet, you are being pushed off your geodesic. You are being forced to take a path that is not the straightest one available in space-time. When you are standing still on the ground, the Earth's surface is constantly pushing up against you, preventing you from following your natural geodesic toward the center of the Earth. You only feel gravity when you are being stopped from following the geometry of space-time. This is why astronauts in the International Space Station feel weightless. They aren't in a place where gravity doesn't exist. The Earth's gravity at that altitude is still about 90% as strong as it is on the ground. They feel weightless because they are allowed to follow their geodesic. They are in a state of perpetual free fall, moving along the natural curved path that space-time has laid out for them. In that state, the force of gravity vanishes because they are no longer fighting the architecture. Understanding geodesics allows us to see the universe as a perfectly efficient system. Nothing is forced to happen. The planets don't need to be pushed to stay in orbit. The universe doesn't need to expend energy to keep the stars together. It all happens automatically because of the shape of the container. The architecture of space-time provides the tracks, and matter simply follows them. This geometric view also bridges the gap between the very large and the very small. While we use geodesics to describe the motion of galaxies, the same principles apply to every particle in existence. We are all navigating a landscape of invisible curves, guided by a geometry that was set in motion at the beginning of time. Our lives are a sequence of geodesics, a journey through a four-dimensional map where every turn is a reflection of the mass and energy of the world around us. We often think of gravity as something we can't see, an invisible spirit that haunts the cosmos. But Einstein taught us that we see gravity every single day. We see it in the curve of a planet's surface, in the way a ball arches through the air, and in the very fact that the stars shine in the night sky. Gravity is not a ghost. It is the geometry of spacetime made visible. It is the physical structure of reality expressing itself. When we look at a photograph of a distant galaxy cluster, we are looking at a masterclass in cosmic architecture. We see hundreds of billions of stars held together in a majestic spiral or a shimmering elliptical cloud. What holds them there? It isn't a magical glue. It is the fact that the collective mass of those stars, along with the invisible dark matter that surrounds them, has carved a massive, complex valley into the fabric of the universe. The stars are simply the inhabitants of that valley, gathered in the lowest, most stable points of the curve. Even the light from those stars is a testament to geometry. We mentioned gravitational lensing earlier, but its implications are profound. When we see a mirage in deep space, a distant galaxy distorted into a glowing ring, we are seeing the curvature of space-time acting as a lens. We are literally seeing the dent in the universe created by mass. Gravity is no longer an abstract concept. It is something we can map, measure, and photograph. This geometric understanding also changes how we view time. Because space and time are one fabric, when space is warped, time is warped as well. Near a massive object, where the curvature is steep, time actually flows more slowly. A clock on the surface of the sun would tick slower than a clock on Earth. A clock in deep space, far from any mass, would tick the fastest of all. This is not a mechanical error. It is a property of the architecture. Gravity is the stretching of time just as much as it is the bending of space. This means that we are living in a universe of varying temporal densities. In the valleys of space-time, life moves a little slower. In the high plains, it moves faster. We don't notice this on Earth because the curvature created by our planet is relatively gentle, but it is there, measurable by our most sensitive instruments. Our GPS satellites, for example, have to account for the fact that time moves slightly faster in orbit than it does on the ground. If they didn't, the geometry would be off, and our maps would fail. Gravity is a practical reality that we navigate every second of our lives. The beauty of Einstein's vision is that it takes the most mysterious force in the universe and makes it a matter of shape. It turns physics into art. The universe is not a chaotic collection of pulls and pushes. It is a meticulously designed structure. The stars and planets are not just residents. They are the sculptors of their own environment. They create the very paths they walk upon. As we move forward in our journey, we must keep this image in mind. A universe that is a single, flexible fabric, where matter, energy, space and time are all intertwined. Gravity is the language that this fabric speaks. It is the way the universe tells us where we are and where we are going. By understanding the curvature of space-time, we are not just learning about gravity, we are learning to read the blueprint of creation. We are seeing the invisible architecture that holds the stars in their place and the very seconds of our lives in their flow. To understand the architecture of our universe, we must first abandon the comfort of the clock on the wall. We have been raised to believe that time is a universal constant, a steady, unyielding river that flows at the same rate for everyone, everywhere. We imagine a now that exists simultaneously across the entire cosmos, a cosmic heartbeat that ticks in unison for a child on Earth and a star in the Andromeda galaxy. But this intuitive version of time is a beautiful illusion, a byproduct of our slow-moving lives on a small, quiet planet. In the true architecture of space-time, time is not a fixed background. It is a flexible dimension, as malleable as a piece of clay, and the primary tool that shapes it is motion. This journey into the elasticity of time begins with a single unbreakable law: the speed of light. In our everyday experience, speeds are additive. If you are on a train moving at 60 kilometers per hour and you throw a ball forward at 20 kilometers per hour, a person standing on the platform sees the ball moving at 80 kilometers per hour. It makes perfect sense. But the universe does not work this way when it comes to light. Whether you are standing still, running toward a light beam, or flying away from it at half the speed of light, you will always measure that beam of light traveling at exactly 299,792 kilometers per second. Light never speeds up, and it never slows down. It is the absolute anchor of reality. When Albert Einstein grasped this constant nature of light, he realized something terrifying and profound. If the speed of light must remain the same for every observer, no matter how fast they are moving, then something else has to give. Speed is simply distance divided by time. If the speed is fixed, then distance and time themselves must change to keep the equation balanced. This was the moment the absolute universe of Newton died and the relative universe was born. Motion through space was no longer just a change in position. It became a direct manipulation of time. Imagine a simple clock, not made of gears and springs, but of two mirrors and a single photon of light bouncing between them. Each bounce represents one tick of the clock. If this clock is sitting still on a table in front of you, the photon moves straight up and straight down. But now imagine that clock is placed on a spaceship flying past you at a significant fraction of the speed of light. As you watch the clock zoom by, the photon is no longer moving just up and down, it is moving diagonally. Because the clock is moving forward, the photon has to travel a much longer zigzag path to hit the mirrors. Now remember the law. Light cannot speed up to cover that extra distance. It must travel at its one constant speed. Because the photon on the moving clock has to travel a longer path at the same speed, it takes longer to complete a single tick. To you, standing on the ground, the clock on the spaceship is literally running slower. The very seconds on that ship are being stretched out. This isn't a mechanical trick. The actual fabric of time on that ship has been elongated by its motion through space. This is time dilation, and it is the first great secret of the architecture of space-time. This means that the faster you move through space, the slower you move through time. They are two parts of the same whole. Think of it as a cosmic budget. Every object in the universe is constantly moving through the four dimensions of space-time at one fixed speed, the speed of light. If you are sitting perfectly still, all of your movement is directed through the dimension of time. You age at the maximum possible rate, But as soon as you start moving through space, you have to divert some of that movement away from time to pay for your spatial travel. The faster you go through the 3 dimensions of space, the less speed you have left for the dimension of time. If you could somehow reach the speed of light itself, your movement through time would drop to 0. You would become ageless, frozen in a single, eternal moment. This isn't just a theoretical curiosity. We have proven it with the most rigorous precision. We have taken atomic clocks, instruments so accurate they wouldn't lose a second in millions of years, and flown them around the world on commercial jets. When they returned, they were slightly behind the clocks that stayed on the ground. We see it in subatomic particles called muons, which are created in the upper atmosphere. Muons are unstable and should decay in a tiny fraction of a second, far too quickly to reach the Earth's surface. But because they travel at nearly the speed of light, their internal clocks slow down so much that they survive long enough to be detected by us. To the muon, its life is brief. To us, its life is extended by the sheer velocity of its journey. This realization shatters our concept of a universal now. If your motion dictates the speed of your time, then 2 people moving at different speeds will never agree on how much time has passed, or even when an event occurred. In the architecture of space-time, time is personal. It is a private experience dictated by your path through the cosmos. We are all living in our own temporal bubbles, slightly out of sync with everyone else. The deeper implication of this is that space and time are not just connected, they are interchangeable. They are like the length and width of a rectangle. If you rotate the rectangle, some of the length becomes width, and some of the width becomes length. Motion is essentially a rotation in space-time. When you move through space, you are rotating your perspective so that some of your time becomes space and some of your space becomes time. This is why we must speak of space-time as a single fabric. You cannot touch one without affecting the other. The architecture of the universe is a 4-dimensional landscape where our motion acts as a sculptor, stretching and compressing the seconds of our lives. We are not just travelers through a void, we are weavers of time. Every step we take, every flight we board, and every cosmic journey we envision is a manipulation of the very foundation of reality. By understanding that motion slows time, we stop being victims of the clock and start being participants in the geometric design of the universe. We discover that the second is not a prison, but a flexible boundary, and that the faster we dare to venture into the vastness of space, the more we find ourselves treading on the very shores of eternity. To live in the universe of relativity is to accept that the very tools we use to measure reality, the ruler and the stopwatch, are themselves made of shadows and light. We have already seen how motion through space acts as a sculptor of time, slowing the heartbeat of the traveler as they venture closer to the ultimate speed. But the architecture of space-time is even more intricate than a simple slowing of clocks. As we move through this 4-dimensional fabric, the dimensions of space themselves begin to yield. Just as time stretches, space must contract. This is the phenomenon of length contraction, and it is the necessary partner to time dilation, ensuring that the speed of light remains the absolute unchanging sovereign of the cosmos. Imagine you are embarking on a journey to a star system 10 light-years away. To an observer on Earth, you are traveling in a magnificent vessel at 99% of the speed of light. From the perspective of those left behind, the journey will take just over 10 years. They watch your ship through their telescopes, and because of your incredible speed, they see your clocks ticking with a ghostly slowness. To them, you have spent only a little more than a year in transit. But if time has slowed down for you, how do you perceive the distance? If you only experienced 1 year of travel, but the star is 10 light-years away, a simple calculation would suggest you traveled 10 times faster than light. But we know this is impossible. The universe has a solution, a geometric sleight of hand. For you, the traveller, the distance to the star is no longer 10 light-years. The very space between the Earth and your destination has shriveled. For you, the journey is only about 1.5 light-years long. The universe has shortened the road to match your slowed-down clock. This is the shrinking yardstick of relativity. When you move through the architecture of space-time, you are not just passing through a static void. You are interacting with a medium that responds to your velocity. In the direction of your motion, the universe flattens. A spherical planet, if passed at near light speeds, would appear to you as a thin, compressed pancake. A long, slender rocket would appear to a stationary observer as a short, stubby craft. This is not an optical illusion, nor is it a physical crushing of atoms. It is a fundamental alteration of the geometry of space. Length and time are two sides of the same coin, and they balance one another perfectly to ensure that light speed is never exceeded. This symmetry is the very soul of the space-time fabric. But the architecture of space-time is not only affected by how fast we move, it is shaped even more profoundly by the presence of mass. This is where we transition from the special relativity of motion to the general relativity of curvature. As we established, mass tells space-time how to curve, and curvature tells matter how to move. But this curvature does not just bend the lanes of space, it thickens the flow of time. This is gravitational time dilation, a concept that proves time is heavier near the heart of a world. Consider the Earth beneath your feet. It is a massive body, and as it sits in the fabric of space-time, it creates a gentle, persistent well. Because space and time are woven together, the Earth's mass is not just pulling on the where of your existence, but the when. Near the surface of our planet, the curvature of space-time is more intense than it is out in the dark reaches of orbit. In this more intense curvature, time itself is forced to flow more slowly. This means that your feet, being closer to the center of the Earth, are actually aging slightly slower than your head. The difference is infinitesimal, billionths of a second over a lifetime. But it is real. If we were to take this to an extreme, the effect becomes breathtaking. Imagine two twins. One decides to live on the surface of a neutron star, an object so dense that a teaspoon of its material would weigh as much as a mountain. The other twin stays in the quiet, flat space of deep vacuum. For the twin on the neutron star, the weight of gravity is so immense that space-time is stretched to a near breaking point. Time would flow at perhaps half the rate it does for the twin in deep space. For every year the mountain-dwelling twin experiences, 2 years would pass for their sibling. Gravity in this sense is like a cosmic anchor, dragging on the seconds and minutes, preventing them from slipping away as quickly as they do in the shallows of space. This reveals a profound truth about the architecture of reality. Gravity is the stretching of time, just as much as it is the bending of space. We cannot have one without the other. When we see a planet orbiting a star, we are seeing it navigate a region where space is curved and time is slowed. The orbit is the path of most time. The The geodesic that allows the object to move through the four-dimensional landscape while experiencing the maximum possible passage of its own internal clock. The universe is not a chaotic tumble. It is a meticulously balanced geometric machine that seeks the path of least resistance through a distorted medium. We see the practical evidence of this every time we use a modern smartphone to find our way. High above us, the satellites of the global positioning system are constant witnesses to the elasticity of space-time. They are moving at high speeds, thousands of kilometers per hour, which should cause their clocks to slow down relative to ours due to motion. However, they're also far away from the Earth's mass, where the curvature of space-time is weaker, which causes their clocks to tick faster than ours. These two effects, one pulling time slower, the other pushing it faster, do not cancel out. The gravitational effect is stronger. Every day, the clocks on those satellites gain about 38 microseconds compared to the clocks on the ground. 38 millionths of a second might seem like nothing, but if the engineers didn't program Einstein's equations into the satellite's computers, your GPS would be off by 10 kilometers within a single day. The architecture of space-time is not a distant theory. It is a literal calculation we must make to survive and navigate our modern world. This relationship between motion, mass and time tells us that we are not living in a world of fixed things. We are living in a world of flows. We are embedded in a four-dimensional manifold where every movement we make and every massive object we encounter reshapes the measurements of our lives. If you could travel fast enough or stand near a heavy enough object, you could look back at the Earth and see its history unfold like a fast-forwarded movie. You could witness the rise and fall of civilizations in what felt to you like an afternoon stroll. This is the ultimate consequence of living within a curved structure. We are participants in a grand elastic design. We have learned that length is not a property of an object, but a relationship between the object and the observer's motion. We have learned that a second is not a universal unit, but a measure of the local curvature of the universe. The architecture of space-time is a living, breathing thing, an invisible scaffolding that stretches and shrinks, slows and accelerates, all to maintain the perfect, unwavering harmony of the light. By understanding these consequences, we begin to see the universe not as a static stage, but as a fluid, dynamic masterpiece where time and space are the very colors being used to paint the story of existence. To truly grasp the architecture of space-time, we must look beyond the mechanical ticking of the watches on our wrists and consider the cosmic heartbeat that governs every atom in the universe. We have explored the concepts of stretching and shrinking, but now we must confront the most startling reality of all: that time itself is a local phenomenon. There is no master clock sitting at the center of the universe dictating a single synchronized rhythm for all of existence. Instead, the universe is a mosaic of billions of different timelines, each one ticking at a pace determined by the local conditions of motion and mass. To understand why clocks tick differently is to understand the very friction of reality. The way the fabric of space-time resists and reshapes the passage of the moments we call our lives. Think of time not as a rigid iron rail, but as a fluid stream. In the quiet, empty reaches of the deep void, far from the influence of any star or galaxy, this stream flows at its swiftest and most unobstructed rate. This is the baseline of time, the purest expression of the fourth dimension. But as soon as we introduce the two great sculptors of the cosmos, velocity and gravity, this fluid begins to thicken, to churn, and to slow. These are not merely effects on the machinery of a clock. They are changes to the very rate at which physical processes occur. A heart beats slower, a cell divides more cautiously, and an atom vibrates with a lower frequency. Let us first examine the clock of the traveller, governed by the law of motion. We must envision the universe as having a total speed limit, which we know as the speed of light, approximately 300,000 kilometers per second. Every object is always moving through the four combined dimensions of space-time at this exact speed. When you're sitting perfectly still in your chair, you're not truly stationary. You're hurtling through the dimension of time at the maximum possible velocity. All of your motion budget is being spent on aging. However, the moment you begin to move through the three dimensions of space, whether you are walking, driving, or flying in a rocket, you are forced to divert some of that budget. You are taking speed away from time and giving it to space. As you move faster and faster, your progress through the temporal dimension must slow down to compensate. If you were to travel at 90% of the speed of light, your speed through time would drop significantly. To an observer standing still, your movements would appear sluggish, as if you were moving through a world made of thick honey. This is kinematic time dilation. It is the reason why a clock on a speeding train ticks a fraction of a second slower than the clock in the station. In our daily lives, these speeds are so small compared to the speed of light that the difference is invisible to our biological senses. But the architecture does not care about our limitations. The law is absolute. At the speed of light, the diversion is total. All speed is given to space, and none is left for time. A photon of light, born in the heart of a distant star, experiences no time at all. From its own perspective, its birth and its eventual absorption by your eye happen at the exact same instant, even if that journey spanned billions of light years. To light, time does not exist. It is only for those of us who move slower than light that the seconds have meaning. Now we must consider the second sculptor, gravity. If motion is a diversion of time, gravity is a physical compression of it. We have visualized space-time as a fabric warped by mass, a trampoline weighed down by the heavy spheres of planets and stars. But we must remember that time is the very thread of that fabric. When a massive object like the Earth creates a curve in space, it is also pulling on the temporal dimension. The deeper you go into a gravitational well, the more compressed the space-time becomes. In this high-density region, time is forced to move more slowly. It is as if the very presence of mass creates a kind of temporal drag. This means that gravity is not just a force that holds your feet to the ground. It is a force that anchors you in time. If you were to stand on the surface of the sun, ignoring for a moment the impossible heat, your clock would tick measurably slower than it does on Earth. The sun's immense mass, which is 333,000 times that of our planet, creates a much deeper valley in space-time. In that valley, the rhythm of reality is slower. If you could look out from the sun's surface toward the Earth, you would see the earthly clocks racing ahead of you. To you, the people on Earth would appear to be living in fast forward. To them, you would be a figure of statuesque slowness. This phenomenon, gravitational time dilation, creates a universe of vertical time. Time literally passes at different rates, depending on your altitude. Scientists have proven this by placing incredibly precise optical lattice clocks at different heights. Even a difference of just 1 foot in elevation, the height of a single step, results in a measurable difference in the passage of time. The clock closer to the floor, being deeper in the Earth's gravitational well, ticks slower than the clock on the table. Over the course of billions of years, the core of the Earth is actually younger than its crust by about 2.5 years. This is not a metaphor. It is the physical architecture of our world. We are living on a planet that is literally younger in its center than on its surface. The most profound demonstration of these two conflicting effects occurs in the fleet of satellites that form the global positioning system. These satellites are the modern-day cathedrals of relativity, and their survival depends on our understanding of how clocks break. Each satellite orbits the Earth at a speed of about 14,000 kilometers per hour. This velocity, according to the laws of motion, causes their internal atomic clocks to tick slower than clocks on the ground by about 7 microseconds every day. However, these satellites are also 20,000 kilometers above the Earth's surface. At that altitude, the curvature of space-time is much weaker than it is at sea level. Because they are higher up in the gravitational well, time flows faster for them. This gravitational effect causes their clocks to gain about 45 microseconds every day. When we combine these two effects, the 7 microseconds lost to speed and the 45 microseconds gained by gravity, we find that the clocks on the GPS satellites tick faster than our clocks on Earth by 38 microseconds every day. If the scientists and engineers had not accounted for this, if they had assumed that time was the same everywhere as Newton believed, the entire system would fail within minutes. 38 microseconds may seem like a tiny interval, but light travels about 11 kilometers in that time. Within a single day, the GPS coordinates on your phone would be off by more than 10 kilometers, and by the end of the week, the system would be entirely useless. Every time you use your phone to find a nearby restaurant or navigate a new city, you are using a device that must constantly correct for the fact that time is not a constant. You are holding a piece of evidence for the curvature of the universe in the palm of your hand. This realization leads us to a startling conclusion. The now that we feel so strongly is an entirely local experience. There is no universal moment that we all share. Because our motion and our position in a gravitational field are always unique, our experience of time is unique. If you and a friend both synchronized your watches and then one of you took a flight across the ocean while the other stayed at home, you would no longer be in temporal sync when you reunited. The difference would be small, perhaps a few billionths of a second, but you would have traveled through different amounts of time. You would be, in a very real sense, slightly out of phase with one another. In the grand architecture of space-time, clocks are not measuring a pre-existing time that exists outside of matter. They are measuring the local density of the fourth dimension. The universe is a vast landscape of varying temporal speeds. Near a black hole, time slows to a near standstill. In the vast voids between galaxies, it rushes forward with unbridled speed. We are all drifting through this landscape, navigating the peaks and valleys of the temporal terrain. By understanding that clocks tick differently, we stop seeing time as a master and start seeing it as a dimension, a physical, flexible part of the structure of the cosmos. We realize that we are not just moving through space, but we are also constantly negotiating our place in time, guided by the silent, invisible curves of the world around us. Perhaps the most deeply ingrained intuition we possess as human beings is the sense of a shared now. We feel with an absolute and unwavering certainty that as we sit in this moment, the rest of the universe is experiencing the same moment with us. We imagine a thin, invisible sheet of existence, a cosmic slice of the present, that slides through the four-dimensional block of the universe, bringing everything into being simultaneously. In our minds, if we could freeze the entire cosmos at this very heartbeat, we would see every star, every planet, and every living creature frozen in their own version of this instant. But the architecture of space-time has no room for such a slice. One of the most radical and unsettling discoveries of relativity is that now is not a universal fact. It is a subjective perspective, a trick of the light, and it depends entirely on how you are moving through the fabric of reality. To understand why the present is an illusion, we must return to our anchor, the speed of light. Because light takes time to travel, we are always looking into the past. We see the moon as it was 1¼ seconds ago. We see the sun as it was 8 minutes ago. We see the distant stars as they were centuries or millennia ago. This delay is familiar to us, but we usually dismiss it as a mere limitation of our senses. We assume that there is a true present happening right now at those distant locations, and we are simply waiting for the news to arrive. But Einstein proved that there is no true present. If you and an observer are moving relative to each other, you will disagree, fundamentally and correctly, on which events are happening now. Imagine a classic thought experiment. Suppose you are standing in the exact middle of a very long, high-speed train moving through a station. On the platform, a friend is watching you zoom by. At the precise moment you pass your friend, 2 bolts of lightning strike the front and back ends of the train simultaneously from your friend's perspective. Your friend sees the 2 flashes of light reach them at the exact same time and concludes that the 2 strikes happened at the same moment. But what do you see on the moving train? As the lightning strikes, you are rushing toward the light coming from the front of the train and away from the light coming from the back. Because the speed of light is constant, the flash from the front of the train reaches your eyes first. A split second later, the flash from the back arrives. From your perspective, sitting inside that moving frame of reference, the event at the front of the train happened before the event at the back. You are not wrong, and your friend on the platform is not wrong. Both of you are describing the physical reality of your own space-time. The now of your friend includes both lightning strikes. Your now includes only the first one. This is the relativity of simultaneity. It tells us that there is no objective way to slice the universe into past, present, and future. If you change your speed, you tilt your slice of now. It is as if the universe is a giant loaf of bread, the block universe. One person might slice the loaf perfectly straight, while another person, moving at a different speed, slices it at an angle. Both slices are equally real, but they contain different parts of the loaf. What is the present for you might be the future for someone else, and the past for a third observer. The implications of this tilt are staggering when applied over cosmic distances. This is often illustrated by the Andromeda paradox. Imagine 2 people walking past each other on a sidewalk on Earth. One is walking toward the Andromeda galaxy, and the other is walking away from it. Because their speeds are different, their slices of now are tilted relative to each other. At the distance of Andromeda, about 2,500,000 light-years away, this tiny tilt on Earth translates into a massive discrepancy in time. For the person walking toward Andromeda, their now might include a moment where an alien fleet has already launched an invasion. For the person walking away, Their now might be a moment days or even weeks earlier, when the alien commanders are still debating whether to go to war. Both versions of the present in Andromeda are equally valid for the observers on Earth. If the present can contain events that haven't happened yet for someone else, then those future events must already exist in some form within the architecture of space-time. This leads us to the concept of the block universe. In this view, the past is not gone, and the future is not unwritten. Instead, space-time is a four-dimensional structure where every moment that has ever happened and every moment that will ever happen is already there, laid out like a landscape. Our perception of time as a moving now is simply our consciousness travelling along our personal world line through this static structure. We are like someone walking through a forest with a small flashlight. We can only see the trees immediately in front of us. That is our present. But the trees we have passed still exist in the dark behind us, and the trees we haven't reached yet are already standing in the dark ahead. This shattering of the now reshapes our intuitive understanding of time. It suggests that our sense of a shared flowing present is a result of our proximity to one another and our relatively slow speeds. Because we all live on the same planet and move at speeds that are negligible compared to the speed of light, our slices of now are almost perfectly aligned. We agree on the timing of events because our tilt is so small that it's imperceptible. But on the scale of the cosmos, the architecture of space-time reveals a much more complex and eternal design. The lack of a universal now means that the universe does not happen in the way we think it does. It simply is. The architecture of space-time is a finished masterpiece, and we are the ones discovering it, page by page. This realization removes the sting of the passing second. If there is no universal now, then the past is not a graveyard of lost moments, but a permanent part of the cosmic structure. Every laugh, every discovery, and every star that has ever burned is still there, eternally woven into the fabric. By understanding that now is an illusion, we begin to see the true majesty of the cosmic design. A structure where time and space are not fleeting shadows, but the solid, unchanging pillars of reality. We are participants in an eternal architecture, finding our way through a landscape where every now is just a single beautiful perspective on a much larger and more profound whole. We have travelled through the stretching of seconds and the shrinking of yards, through the thickness of time near the earth and the thinness of the void. We have witnessed the shattering of the universal now and the birth of a reality where every observer carries their own private rhythm. But now we must step back from the mechanics of clocks and rulers to see the grandest transformation of all. We must ask how this architecture, this four-dimensional fabric of space-time, forever changes what it means to be a human being living within the flow of history. The transition from Newton's clockwork universe to Einstein's relative one is not just a change in physics. It is a profound philosophical shift that redefines the very nature of our existence, our memories, and our destiny. For thousands of years, our intuition told us that time was a ghost, a fleeting, intangible thing that was always vanishing. We saw ourselves as existing only in the present, a razor-thin boundary between a past that no longer existed and a future that had not yet been born. This view, which philosophers call presentism, feels right to our biological senses. We remember the past, but we cannot visit it. We anticipate the future, but we cannot know it. We feel like passengers on a one-way train, watching the scenery disappear behind us forever. But the architecture of space-time tells a very different story. It tells us that the scenery is not disappearing at all. It tells us that the train is not moving. It is the track itself that is the reality. In the wake of Einstein's discoveries, his teacher, Hermann Minkowski, famously declared that henceforth space by itself and time by itself were doomed to fade away into mere shadows, and only a kind of union of the two would preserve an independent reality. This union is the block universe, a concept that fundamentally reshapes our intuitive understanding of time. In this view, time is not a sequence of events that happen and then vanish. It is a physical dimension, as solid and enduring as the three dimensions of space. Just as the city of New York doesn't cease to exist simply because you are currently in London, the year 1925 doesn't cease to exist simply because your consciousness is currently at the coordinate of 2025. This means that the architecture of the universe is an eternal landscape. Every moment of your life, your first breath, your greatest achievement, your quietest reflection, is a permanent coordinate in the four-dimensional manifold. You are not a fleeting spark in the dark. You are a continuous four-dimensional structure, a world line woven into the very fabric of the cosmos. If you could step outside of space-time and look back at the universe, you wouldn't see things happening. You would see a shimmering crystalline structure where every event is fixed in its place. You would see the Earth as a long, spiraling tube as it circles the sun through time. You would see yourself as a complex, branching path stretching from birth to death. This realization offers a profound comfort that our intuition denies us. In the Newtonian world, the past is a graveyard. When a loved one passes away, they are gone from the universe. But in the architecture of space-time, they are never gone. They are simply located at a different set of temporal coordinates. Their life is an eternal part of the block. As Einstein himself wrote to the family of a deceased friend, "For us, believing physicists, the distinction between past, present and future is only a stubbornly persistent illusion." To understand the architecture is to realize that now is merely a perspective, like the word here. When you say you are here, you aren't suggesting that there doesn't exist. You are simply identifying your current location. Time is no different. But if the universe is a static block, why do we feel a flow? Why do we perceive time as moving forward? This is where the physics of the architecture meets the biology of the brain. Our perception of the flow of time is likely an internal psychological process rather than a fundamental property of the universe itself. We are complex biological machines designed by evolution to survive, and survival requires us to process information in a specific direction, from lower entropy to higher entropy. Our brains create the feeling of a moving present to help us navigate the world line we are traveling. We are like readers of a book. To the reader, the story unfolds, page by page, full of surprises and tension. But the book itself is a finished object. Every word, from the first sentence to the last, is already written and exists simultaneously between the covers. We are the readers of the cosmic book, and the architecture of space-time is the paper and ink. This shift in understanding also forces us to reconsider the concept of destiny. In a world where the future already exists as a set of coordinates in the block, the idea of free will becomes a deep and difficult puzzle. If your life is a fixed world line in a four-dimensional structure, is the future already written? The architecture suggests a universe that is determined in its geometry. Yet our local experience feels entirely open and undecided. This tension is one of the great frontiers of modern thought. Perhaps the future is just as real as the past, but our inability to see it is what gives our choices their meaning. We are discovering our path, even if the path is already laid out in the silent, eternal architecture of the cosmos. Furthermore, relativity teaches us that the universe is a unified whole. We cannot talk about space without talking about time, and we cannot talk about matter without talking about the curvature it creates. This interconnectedness means that we are not separate from the universe. We are not observers standing on the sidelines of reality. We are the fabric itself, expressing itself in a particular form. Every atom in our bodies is a tiny warp in the space-time manifold. Every thought we have is an event at a specific coordinate. We are as much a part of the architecture as the stars and the black holes. As we conclude this exploration of motion and relativity, we must look at the night sky with new eyes. We are no longer looking at a distant, static theatre. We are looking at a dynamic, elastic and eternal structure. We see stars that may have died thousands of years ago, yet their light is now for us. We see galaxies whose present we can never know. We realize that the universe is a vast, shimmering tapestry of different times and different perspectives, all held together by the unwavering constancy of light. The architecture of space-time is the ultimate canvas of reality. It is a design that is both flexible and firm, both personal and universal. It tells us that time is not our enemy, but our environment. It tells us that we are not drifting through a void, but navigating a meticulously structured landscape. By understanding how motion and gravity reshape time, we have learned to see the world not as a sequence of disappearing moments, but as an enduring masterpiece. We are participants in a grand geometric design, finding our place within a structure that is far more magnificent, far more enduring, and far more connected than we ever dared to imagine. In the architecture of space-time, nothing is ever truly lost, and every moment is a permanent part of the story of the stars. To understand the architecture of space-time is to eventually confront its breaking point. We have seen how the sun curves the fabric of the universe into a gentle, life-sustaining valley, and how galaxies form vast, shimmering basins that hold billions of stars in their embrace. But the universe also contains regions where the architecture does not merely bend, it buckles, it collapses, it tears. These are the black holes, the most extreme manifestations of gravity in existence. They are the places where the geometry of space-time is pushed to such an absolute limit that the laws of physics as we know them begin to scream in protest. The birth of such a monster is a tragedy of cosmic proportions. It begins with a star, perhaps 20 or 30 times the mass of our sun. For millions of years, this star lives in a state of delicate, violent balance. In its core, the crushing weight of gravity tries to pull everything inward, but it is held back by the outward pressure of nuclear fusion, the same process that makes our sun shine. But eventually, the fuel runs out. The fire dies. In a fraction of a second, gravity wins the war that has lasted for eons. The star's core collapses inward at a significant fraction of the speed of light. If the star is massive enough, there is nothing in the known universe that can stop this collapse. Not the pressure of atoms, not the resistance of subatomic particles. The mass is crushed into a smaller and smaller volume, and as it does, the curvature of the surrounding space-time becomes increasingly violent. Imagine our rubber sheet again. Instead of a bowling ball creating a dip, imagine a needle-thin point of infinite weight pressing down on the fabric. The slope becomes steeper and steeper, the valley turns into a canyon, and then, finally, into a bottomless pit. A black hole is not an object in the traditional sense. It is a region of space-time where the curvature has become so extreme that it has effectively cut itself off from the rest of the universe. It is a localized end to the architecture. When we speak of a black hole, we are speaking of a place where the density of gravity is so high that the very paths of light, the geodesics we discussed earlier, all turn inward. There is no longer a path that leads away from the center. To enter a black hole is to enter a part of the cosmic design that has been permanently rewritten. It is the ultimate precipice, a place where the fabric of reality is stretched beyond its elastic limit, revealing the terrifying power of mass when it is allowed to have its way without restraint. If a black hole is an infinite pit, then the event horizon is the lip of that pit. It is perhaps the most misunderstood boundary in the cosmos. It is not a solid surface like the crust of a planet. It is not a wall of fire or a swirling cloud of gas. The event horizon is a mathematical ghost, a boundary of pure geometry. It is the point in space-time where the escape velocity equals the speed of light. Imagine you are rowing a boat on a calm river that leads toward a massive waterfall. Far upstream, the current is gentle. You can row against it easily. As you get closer to the edge, the water moves faster. Eventually, you reach a line where the water is moving exactly as fast as you can row. If you cross that line, it doesn't matter how hard you struggle. The river is now faster than your maximum speed. You're doomed to go over the falls. The event horizon is that line for light. Because nothing in the universe can travel faster than light, anything that crosses this horizon, be it an atom, a spaceship, or a single photon, is forever trapped. The architecture of space-time inside the horizon is so warped that every possible future path leads toward the center. To turn around and leave would require you to move faster than light, which is to say, you would have to break the very foundation of reality. For an outside observer, the event horizon is a place of eternal silence. Because light cannot escape, we can never see what happens inside. We only see the silhouette of the black hole against the glowing gas and stars behind it. Information itself is censored by the geometry. This is the ultimate do not enter sign of the universe. It marks the boundary between the known world, where light can carry news, and a hidden realm that has departed from our causal reach. The event horizon is the final veil of the architecture, a threshold that divides existence into what can be shared and what must be lost forever. As we move deeper into the black hole, past the event horizon, we reach the heart of the darkness, the singularity. If the event horizon is the boundary of the architecture, the singularity is its destruction. According to the mathematics of Einstein's general relativity, as the mass of the collapsed star continues to fall inward, it is crushed into a point of zero volume and infinite density. This is where the architecture of space-time reaches its most profound crisis. In our earlier discussions, we visualized space-time as a smooth, continuous fabric. But at the singularity, the fabric is punctured. The curvature becomes infinite. The grid lines of time and space don't just bend, they vanish. When a physical theory predicts an infinite value, it is a signal from the universe that our understanding has failed. The singularity is the place where our current laws of physics return an error message. In this point of infinite density, the very concepts of where and when lose their meaning. We believe that at these extreme scales, the smooth geometry of general relativity must meet the chaotic, grainy reality of quantum mechanics. But currently, these two pillars of science do not speak the same language. The singularity is a blind spot in the cosmic blueprint. It suggests that there is a deeper layer of the architecture that we have yet to discover. A quantum gravity that prevents infinities and explains what happens when space and time are crushed out of existence. The singularity is a reminder that the universe is not obligated to make sense to us. It is the place where the map ends and the territory becomes unknowable. It is the most extreme point in the structure, a needle-sharp reality that defies every intuition we have ever held about the nature of a solid world. It is the ultimate mystery hidden away behind the event horizon, daring us to find a new way to describe the foundation of existence. Perhaps the most mind-bending aspect of the black hole's architecture occurs the moment you cross the event horizon. In the world we inhabit, space and time are distinct. You have freedom in space. You can move left or right, up or down, forward or backward. But you have no freedom in time. You are relentlessly dragged from the past into the future at a rate of 1 second per second. Inside a black hole, however, the extreme curvature causes space and time to effectively exchange roles. As you fall past the event horizon, the radial direction, the path toward the center, is no longer just a direction in space. Because of the overwhelming warp of the geometry, the center of the black hole actually becomes your future. Just as you cannot turn around and walk into yesterday in our world, you cannot turn around and move away from the singularity inside a black hole. The singularity is no longer a place you are going to. It is a time you are approaching. Every heartbeat, every movement of your hand takes you closer to that inevitable future. In this twisted architecture, trying to escape by firing your rockets is as futile as trying to stop the clock from ticking. In fact, in some scenarios, the harder you struggle to stay away from the center, the faster you arrive there, because you are essentially trying to run through a time stream that only flows one way. This reversal is the ultimate triumph of the architecture over the inhabitant. It reveals that the dimensions of our universe are not as rigid as they seem. They are fluid, dependent on the local density of mass and energy. Inside the black hole, the very structure of how things happen is flipped on its head. It is a world where the where becomes when, and the when becomes an inescapable destination. This is the final, most haunting transformation of the fabric, a place where the geometry of the universe traps you not with a force, but with the very flow of time itself. For decades, black holes were thought to be mere mathematical curiosities, monsters in the basement, that Einstein's equations allowed, but that nature would surely never create. But today we know they are everywhere. They sit at the heart of almost every galaxy, including our own. They are the essential anchors of the cosmic architecture. And yet their greatest value to us is not in their power, but in what they reveal about the limits of our own knowledge. Black holes expose the deepest flaws in our theories. They represent the ultimate stress test for the human mind. The information paradox, the question of what happens to the data of an object that falls into a black hole, has forced us to reconsider the very nature of reality. Does the universe remember what it has consumed, or is information truly deleted? Stephen Hawking's discovery that black holes can slowly evaporate through Hawking radiation suggested that even these eternal prisons have a lifespan. This radiation, which comes from the quantum vacuum at the edge of the horizon, hints at a profound connection between the very large and the very small. By studying these extremes, we are forced to build a stronger architecture for our theories. Black holes are the laboratories where we test the strength of space-time. They tell us that our current blueprints, general relativity and quantum mechanics, are incomplete. They are like cracks in a diamond, revealing the underlying structure and the points where it might eventually break. In the end, black holes are the most honest parts of the universe. They do not hide the violence of gravity. They celebrate it. They show us that the architecture of space-time is both incredibly robust and strangely fragile. By looking into the dark, we learn about the light. By studying the places where the fabric of reality tears, we learn how it is woven. Black holes are not just the ends of stars, they are the gateways to the next great revolution in our understanding of the cosmos. They remind us that to truly know the design of the universe, we must be brave enough to look at the points where the design fails. We have traveled to the ends of the universe and into the hearts of darkness. But as we return to the familiar world of our daily lives, we must realize that the architecture of space-time is not just a distant cosmic wonder. It is here, in the room with you. It is the silent companion to every breath you take and every thought you have. We often think of space as a stage and ourselves as the actors, but that is a fundamental misunderstanding. Space-time is not the stage. It is the very substance of our reality. It quietly shapes every moment of our existence, exerting a profound influence on the most ordinary of events. Think of the simple act of pouring a cup of tea. As the liquid falls from the pot to the cup, it is following the curvature of space-time created by the mass of the Earth. The gravity that guides the tea is, as we have learned, the geometry of the world. But it goes deeper. The very atoms that make up the tea, the cup, and your own hands are held together by forces that operate within this four-dimensional framework. The rate at which the tea cools, the way the steam rises, and the very passage of the seconds as you wait for it to be ready are all dictated by the local density and curvature of the universe. We are never truly still. Even when we sit in perfect silence, we are hurtling through the temporal dimension at the speed of light, navigating the subtle ripples and folds of a fabric that was woven billions of years ago. This realization transforms the mundane into the miraculous. We are not just living on a planet. We are nestled within a cosmic design that is so seamless and so pervasive that we usually fail to notice it. The architecture of space-time provides the rules of the game for everything we do. It ensures that cause precedes effect, that light has a speed limit, and that time flows with a majestic, if flexible, persistence. By recognizing the hand of this invisible sculptor, we begin to see the world with new eyes. We realize that the ordinary is actually the extraordinary made manifest, the silent, steady operation of a universe that is meticulously structured down to the smallest fraction of a millimeter and the shortest tick of a clock. One of the most profound shifts in our understanding of the universe is the realization that we are not outside observers looking in. We are not scientists standing on a platform peering at a distant machine. We are participants, inextricably embedded within the very structure we are trying to describe. Every atom in our bodies is a tiny knot in the fabric of space-time. Our mass curves the universe just as much as a star does, albeit on a much humbler scale. When you move, the universe responds. When you exist, you are contributing to the total geometry of the cosmos. This embeddedness means that our consciousness and our physical forms are part of the four-dimensional manifold. We are like threads in a tapestry that have somehow gained the ability to contemplate the pattern. This perspective dissolves the traditional boundary between us and the universe. We are the universe expressing itself through a particular configuration of matter and energy, governed by the same laws of space-time that hold the galaxies together. This connection is not metaphorical. It is a physical, structural truth. This leads to a deep sense of belonging. In a universe that can often seem cold, vast, and indifferent, the architecture of space-time tells us that we are home. We are built from the same lumber as the stars. We follow the same geodesics. We are subject to the same temporal stretches and gravitational pulls. To study the architecture of the cosmos is, in a very real sense, to study our own anatomy. We are the means by which the universe has become aware of its own design. Our role as participants is to be the witnesses of this grand structure, to observe the light, to measure the curves, and to find meaning within the elegant, geometric dance of existence. While our current understanding of space-time as a smooth, four-dimensional fabric has revolutionized science, many physicists believe that this is not the final word. There is a growing suspicion that space-time itself is not fundamental, but emergent. Just as the smooth surface of a lake is actually made of billions of individual water molecules, the fabric of the universe may be made of something even more basic. We are searching for the atoms of space and the moments of time, a deeper architecture that lies beneath the one we can see. Some theories suggest that space-time emerges from quantum entanglement, the strange connection between particles that allows them to influence each other instantly across any distance. Others propose that the universe is like a hologram, where all the information of a three-dimensional volume is actually stored on a two-dimensional surface. In these views, the architecture of space-time is a high-level description, a beautiful approximation of a much more complex and counterintuitive reality. We are like people looking at a digital image. From a distance, it looks like a perfect photograph. But as we zoom in, we begin to see the pixels. The search for this deeper blueprint is the greatest challenge of modern science. It requires us to find a theory of everything that can unite the smooth curves of gravity with the grainy, unpredictable world of the quantum. We are looking for the laws that existed before space and time were even born. This quest reminds us that our current knowledge is a bridge, not a destination. The architecture of the universe is likely far more sophisticated and far more mysterious than we have yet dared to imagine. As we peel back the layers of reality, we find that the invisible framework may be just the beginning of a much larger and more profound story of cosmic emergence. Despite our incredible progress, the architecture of space-time continues to challenge us with profound mysteries. We have discovered that the universe is not just expanding, but that its expansion is accelerating, driven by a mysterious force we call dark energy. We have found that galaxies are held together by an invisible substance we call dark matter. Together, these two dark components make up about 95% of the universe, yet they do not seem to follow the same rules as the ordinary matter and light that we understand. They are like hidden supports in the architecture, vital to the structure but invisible to our current instruments. Furthermore, we still do not fully understand the beginning of the architecture, the Big Bang itself. What happened at the moment when space and time were zero? How did the fabric begin to stretch? Why is the universe so remarkably flat and uniform? These questions haunt our equations and drive our exploration. The architecture of space-time is a masterpiece that we are only beginning to read. Every time we think we have mastered a chapter, the universe reveals a new, unexpected twist. This enduring mystery is not a sign of failure, but a sign of the universe's richness. A cosmos that could be completely understood in a few centuries would be a small and hollow thing. Instead, we live in a reality that is vast enough to keep us curious forever. The challenges that remain, the dark sectors, the quantum gravity, the origins of the Bang, are the frontiers that will define the future of the human spirit. The architecture of space-time is a puzzle that invites us to grow, to think more deeply, and to reach further into the dark than we ever have before. As we conclude our journey through the architecture of space-time, we are left with a final synthesis of thought. We have seen that space and time are one. We have seen that mass and energy are the sculptors of reality. We have seen that motion and gravity are the weavers of time. And we have seen that even the most extreme regions of the cosmos, the black holes, are essential parts of the structural whole. But the most important lesson is how this cosmic design defines us. In learning the architecture of space-time, we discover not only the universe's design, but our own place within it. We are not accidents in a void. We are the conscious expressions of a meticulously ordered system. The very fact that we can understand the curvature of the universe, that we can predict the ticking of a clock near a black hole, and that we can map the echoes of the Big Bang, is a testament to the power of the human mind. We are the bridge between the simple atoms and the complex cosmos. The universe is a grand, four-dimensional masterpiece, and we are its most curious inhabitants. We live our lives within the gentle curves of the Earth, following our personal geodesics through a landscape of time that is both fleeting and eternal. The architecture of space-time is the ultimate home, a structure of unparalleled beauty, precision, and mystery. It is the silent framework that holds everything together, and it is the canvas upon which the story of life is written. As we look up at the stars, we no longer see just points of light in a dark room. We see the peaks of a vast, invisible mountain range. We see the ripples in a cosmic ocean. We see the architecture of reality itself. And in that vision, we find our purpose. To continue exploring, to continue questioning, and to continue marveling at the magnificent design of the world we are so fortunate to inhabit. The journey through space-time is the journey of discovery, and the more we learn about the structure of the heavens, the more we understand the depth and the wonder of being alive.